In this lecture, we'll be discussing section 2.3, which is on the measures of the location of data. So we've already discussed measures of the center of data, what we would commonly refer to as averages. We've talked about measures of variation, so how spread out the data is. And now we're going to talk about measures of location or position. A measure of location provides information about the position or rank of a value of the variable relative to the other values in the data set. We've actually already talked about one measure of location. The median is a measure of location because it's guaranteed to be in the center of the set. It ranks halfway through the data. If we arrange the data from smallest to largest, there would be just as many numbers to the left of the median as there would be to the right of the median, and you're kind of describing a location within the set. But we can generalize and not just focus on the very center, but talk about locations that are 20% of the way up or 90% of the way up. And that leads into the measure of location that I think you're already familiar with, percentiles. Percentiles are a collection of 99 numbers that divide a large set of sorted data into 100 roughly equally sized pieces. Now we're going to do examples with small sets of data, and so we won't get 100 pieces because we won't even have 100 pieces of data. But with a large set of data, percentiles are designed to break the data up into 100 pieces. Sometimes they won't be exactly the same size because the number of pieces of data might not be divisible by 100. And in other cases, there might not be enough variation to actually have 100 slots. Thinking of ACT scores, which only range from 1 to 36, you can't break that up into 100 divisions. But you get the basic idea of how percentiles work. The kth percentile, which we denote by P sub k, the way you read this is you say P, then you say sub, because the k is a subscript, and then k. P sub k is a number such that no more than k% of the data is less than it. Ideally, you'd have exactly k% of the data fall below the kth percentile, but sometimes you can't get the exact percentage you're aiming for, and so the rule of thumb is that you can't have more than k%. Up to, but not more than k% of the data falls below your boundary. So the 60th percentile would ideally have 60% of the data below it, but if you can't achieve exactly 60%, it has to be as close to 60% as you can get without going over. Similarly, if you were finding the 33rd percentile, ideally 33% of the data would fall below that number, but if you can't get exactly 33%, then you go as close to 33% as you can without going over. Now there are two kinds of questions you can ask about percentiles. The easier one is to ask what percentile a specific number falls in. I'm not going to demonstrate that, nor am I going to test you on it. What I do want to show you is determining what the percentiles are. Given a percentile, find the number that would fall at that rank. I'm going to do this with a three-step procedure that's different than what you see in your text. This is not what you'll see in the book. You're welcome to use the book's technique. I prefer this one. This one's more common. I've taught out of quite a few stats books. This is the one that I've seen more often, so this is the one that I like to use. Step 1 when finding the kth percentile. You must arrange the data. In order for a percentile to make sense, the data has to be sorted. And for this particular procedure, you want the data assorted in ascending order. So that means from smallest to largest. Once you have the data arranged, we're going to calculate the location of the kth percentile, and that's why we're going to call this thing L. We do this by taking n times k over 100. So recall that n is the number of data values, what we call the sample size. K comes from the percentile. If you're finding the 53rd percentile, then k is 53. And if you're finding the 18th percentile, then k is 18. And you divide that by 100. This formula isn't really a mystery. It's really just k% of n. Another way to think of this is that you're finding k% of n. We have a list of n numbers, and we want to go k% down the list, so we find k% of the sample size. Now we go to a third step. That step is broken into cases. Sometimes L comes out to a whole number, and sometimes it comes out to a number with a decimal ending. It's actually easier when L is not a whole number. If L is not a whole number, then you round it up to the next largest whole number. This is the position of the kth percentile. So two things here. You're going to have to sometimes fight your instincts to round to the nearest integer and always round up to the next largest. Secondly, that's not telling you the answer, that's telling you the position of the answer. You then count down the list to that position, and whatever data value is in that position, that's the kth percentile. If L is a whole number, then you have to do something similar to what you do for medians when you've got an even number of values. You're going to find the average, the mean of two spots. If L is a whole number, then the kth percentile is the mean of the values in positions L and L plus 1. So you count down to the Lth spot, you find the number right next to it, that would be position L plus 1, and you find the mean of those two values. You add them together and divide by 2. I know this is really abstract, so let's just jump into an example so you can see this in practice. I've got a set of data here, and we're going to find two percentiles for it. I found some electric bill costs per month in various states. And I didn't list all 50 states, which might have been more interesting, but I didn't want the example to take a really long time. So I chose 10 states, and I listed the electric bill costs per month in each of those states. So this first one is $110 per month. This last one is $123 per month. And what I want to find is the 63rd percentile for this data set and the 30th percentile for this data set. In order to do that, you have to put the data in order. Percentiles don't make sense unless you rank the data. Remember that this is a measure of position, which is telling us relative standing, rank. And so you need them in order. And for the process that I've listed here, that ordering has to be done from smallest to largest, ascending order. So let's sort that data in ascending order. Now we have the data sorted from smallest to largest, and we can go on to step 2. Let's do the 63rd percentile first. To find the 63rd percentile, we have to calculate its location, which is found by taking n, the sample size, times k, which comes from the percentile that you're finding, and dividing that by 100. So in this example, n is 10 because there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data, 10 electric bills. N is 10. K for this example is 63, and we divide that by 100. Do that arithmetic and it comes out to 6.3. That's not the answer. You don't get to stop there. Not only do we see that there's a step 3 that we haven't even touched yet, but also 6.3 just doesn't even make sense. Remember that the 63rd percentile should be bigger than approximately 63% of the data. 6.3 doesn't fall anywhere in this list. It's smaller than every piece of data. There's no way that the 63rd percentile of electric bill costs would be $6.30. That's not even a reasonable answer. There's a step 3. Let's go back to the instructions. We see that we're in case 3A because our L is not a whole number. When L is not a whole number, you round it up to the next largest whole number. That's the position of the kth percentile. So I don't have a notation for rounding up. I don't want to use the approximation symbol because we typically use that for rounding to the nearest place. So I'm going to draw this arrow and get 7. And y'all, that ain't the answer either. Don't stop with 7. That's just as ridiculous an answer as 6.3. There's no way 7 is the 63rd percentile. It's smaller than every piece of data. That's giving us the position of the percentile that we want. So starting on the left, we count to the 7th position. 1, 2, 3, 4, 5, 6, 7. Our answer is $123. Well, how many pieces of data is that bigger than? It's bigger than 1, 2, 3, 4, 5, 6 pieces of data. And 6 out of 10 is 60%. So we're really close to 63%. But we can't go over 63%, so picking a number bigger than 123 won't work. Because a number bigger than 123 would be bigger than 7 values, and that would be 70%. That's over the 63 that we were aiming for. We round up because that gets us as large a percentage as we can get without going over. If you rounded this down to 6 and took the 6th number, that would only be bigger than half of the data, 50% of the data, which is not as close to the target as we can get. We round up and we take that spot. Let's do this for the 30th percentile now. Step 1 is to sort the data from smallest to largest. Step 2 is to calculate this L. Let me remind you what the formula says. It says we take n times k and divide by 100. N is the number of values in our set, which is still 10. K comes from the percentile that you're finding. This is the 30th percentile. And we divide that by 100. And 10 times 30 over 100 is 3. This comes out to an integer. That's not the answer. 3 doesn't make sense as a percentile in this set. It's too small. And you don't just go to the third spot either, which seems reasonable. I couldn't get mad at you for making that mistake, except that we've got the steps right in front of us. Case 3b. If L is a whole number, then the kth percentile is the mean of the values in positions L and L plus 1. If it was annoying you that I had misspelled positions, I just fixed that. Anyway, we're going to go to the third position because our L was 3, and then we're going to go to the fourth position because 3 plus 1 is 4, and find the mean of those two spots. So the number in the third position is 103. The number in the fourth position is 104. To find their mean, we add them together and divide by 2, and that comes out to 103.5. It's basically just the number halfway between those. So $103.50. Does that serve as the 30th percentile? Does it do its job? Well, $103.50 is bigger than 3 of the costs in the list, and 3 out of 10 is 30%. It gave us the exact percentage that we want. We don't want to stop with 103 because that's only bigger than 20% of the data, which is good, but we can do better. Now, you could argue that you could pick any number between 103 and 104, and you're absolutely right. The nerds have just agreed to take the number halfway between, which is the same thing that we did for the median in a previous discussion. So those are the two cases that you have to worry about. Now, we've worked these out by hand, and this is where I usually let you off the hook and say, now let's do it with the calculator. But your calculator won't do most percentiles. It's not programmed to do the 63rd percentile or the 30th percentile. We already know it will do the 50th percentile because it can find the median, and there are actually 2 more that it's programmed to do. Let's define those percentiles that the calculator will find, and I'll demonstrate how you do that. Your calculator is programmed to find what we call the quartiles. The first quartile, which we denote by Q sub 1, that's a subscript 1 there, so we say Q sub 1, is the 25th percentile. If you think about the name, it kind of makes sense. The first quartile sounds like it would be in the first quarter of the data, and so it's kind of reasonable that it would be the 25th percentile. The second quartile is the median, and you can call that Q sub 2, but we're already calling it the median, so we're not going to give it that notation. The third quartile, which we denote by Q sub 3, is the 75th percentile. It falls 3/4 of the way down the list. And your calculator is programmed to find these, so I want to demonstrate that. So what I've listed here are the ages of students in a karate class, and we're going to find the 3 quartiles with the calculator. The first quartile, the median, and the third quartile. We could find all of these by hand if we wanted to. To find the median, we know we can organize the data from smallest to largest, find the 2 values in the center because they're an even number of values, and average them. For the first and third quartiles, we can use our new procedure with k equals 25 and k equals 75 respectively. But I want to show you how to do this with the calculator. So we're going to put the data into a list, and I'm going to spare you watching me type it in there. Okay, I've got the 12 values typed into the calculator here. And now I'm going to show you a calculator function that you're going to wish I had shown you earlier in these video lectures. It's called the 1var stats command, and based on the calculator you have, it could have 2 different looks to it. So I'm going to demonstrate this twice. I'm going to quit back to the main screen. To access 1var stats, we're not going to push second and the stat key. We're just going to push stat. And then we're going to scroll over to this calc heading, and you see this first choice says 1var stat. It should probably be pronounced 1var stats because it stands for 1 variable statistics, but I always say 1var stats. This calculates a bunch of 1 variable statistics that you might be interested in. So I'm going to select the 1 key. If you have the newer operating system, you'll get this input screen. The first input is the name of the list that you're using, and I'm using L1, so I'm going to leave it L1. If you're using a different list for some reason, you'll push second and the number of that list. This second input allows you to input a frequency list if you're using a frequency distribution, but we are not. We're using raw data. So I scroll past that to calculate, and that's a command, and we hit enter, and you'll get this output screen. If you look, you'll notice some symbols that you already know, but you don't see any of the things that I've asked for, the first quartile, the median, or the third quartile. I'm going to show you how to get those, but hang tight if you've got the newer operating system, because I also want to demonstrate this for the older operating system. Starting from the list screen again, I push second mode, I press stat, scroll to calc, it's in the same spot, choice 1. But you'll notice that now I don't get that input screen, I just get a 1-var stats prompt on my main screen. You'll also notice that there's no parenthesis next to this like we've seen with previous functions. That's because this function has a default. If you're using L1 like I am, you can just hit the enter key. If you're using a list other than L1, then you push second and the number of the list, and it comes up on the end, and then you hit enter. You don't need parentheses, you just hit enter. But because I'm using L1, and that's the default, I hit the enter key, and I get that same output screen. Now again, you don't see the 3 things that I asked for here. You do see some familiar symbols, but not the quartiles. Note the arrow here, though, indicating that there's more information. So all of us can now scroll down to the bottom. You can do as many as 5 clicks, and you'll see some more information. In particular, I see the first quartile is 18. I see the median is 21. And I see the third quartile is 29. What do these numbers mean? A first quartile of 18 says that the 25th percentile for this data set is 18. So in other words, no more than 25% of the students are less than 18 years old. And if you look carefully, there are only 2 students who are less than 18 years old, and 2 out of 12 is less than 25%. It's not exactly 25% because of the repetition, but it's as close to 25% as we can get without going over. It says the median age in the class is 21. And again, we didn't sort the data from smallest to largest. But analyzing this real quickly, there are 1, 2, 3, 4, 5 teenagers, so they're the 5 youngest. Then the 6th oldest in the class is 20, and the next age is 22, so the median would be halfway between those, and that's the 21. What does the third quartile say? It says that up to 75% of the class is younger than 29 years old. And I encourage you to check that one too, but I'm not going to bore you with counting it through. Now, back to that output screen. Again, you might be irritated, but it didn't just find the quartiles. If you scroll to the top, it also gave us the mean. It uses the notation x bar, which is a little presumptuous because the calculator doesn't know whether this is sample data or population data, but you calculate the mean the same way regardless of what type of data you have, and so it doesn't really matter. It's on us to know which symbol is truly appropriate. It also does the standard deviations, and here's a beautiful thing. It does the calculation as though your data was a sample, and it also does the calculation as though your data was a population. So if you know what type of data you have, you know which one to steal. It even gives you the sample size if you don't know how to count. Scrolling back down to the bottom, not only did it give us the quartiles, but it also gave us the minimum and maximum, which is nice when you're trying to find the range. This 1-var stats will be your best friend on an exam where you're doing a lot of different measures for the same data set. It will knock a bunch of them out, and some of the ones that it won't do, it will at least give you the pieces. Really handy calculator function. Now, along with being measures of position on their own, we can also use the quartiles to define new measures of center and variation. The mid quartile is the mean of the first quartile and the third quartile. So we take the first quartile plus the third quartile and we divide by 2. This mid quartile should fall somewhere in the center. It's not going to be affected by outliers because we don't start on the edges. We start 25% of the way in on each side and then find the average of those 2 numbers. And so this is probably going to fall somewhere in the middle of the set. Because of that, this is actually a measure of center, not a measure of location. This is a quick average that you can find using just 2 pieces of data rather than all of the data, and one of the nice things about it is that it ignores outliers. We haven't formally defined what an outlier is, But by definition, an outlier lives outside of these quartiles. All outliers are either smaller than the first quartile or larger than the third quartile. So you're guaranteed to ignore outliers when you find the mid-quartile. Similarly, we can define a measure of variation that ignores the outliers. The interquartile range is the difference of the third quartile and the first quartile. It's common to abbreviate interquartile range IQR. This isn't a notation, but it's a nice abbreviation. And we just take the third quartile minus the first quartile. And that's measuring how spread out the middle 50% of the data is. So this is a measure of variation. It employs two measures of position in order to describe how spread out the center of the data is. So because we're describing the spread of the data, this is a measure of variation. Again, it ignores outliers. One of the problems we said we have with the range is that it would be easily swayed by outliers. The interquartile range only covers the middle 50% of the data, and so it effectively ignores any outliers. So let's calculate a mid-quartile and an interquartile range, and we may as well do it for the example that we just knocked out. We were looking at the ages of the students in a karate class. We had these 12 ages, and we identified the first quartile and the third quartile for that set of data. The mid-quartile would be the mean of the first and third quartiles. So 18 plus 29 divided by 2. That's 47 divided by 2, which is 23.5. This is supposed to be a measure of center, and you can see that it's at least fairly close to the median. The median is in the dead center. The mid-quartile does a pretty good job of describing the center of this set. The interquartile range is the difference in the quartiles. So we do 29 minus 18, and that's 11. This tells us that the middle 50% of the data is spread out by 11 units, in this case 11 years. It's a little bit harder to get a feel for IQR, just like it is for standard deviation, but it's describing how spread out the data set is. The center of the set is dispersed by 11 units total. Let's do one more demonstration of everything we've talked about in this lecture with one more set of data. We'll start by practicing the 1var stats command and talking about the things that it can do, and then we'll do some percentiles by hand again just to get more practice, because remember, the calculator won't do all of the percentiles on its own. And that will actually give me an excuse to show you one more thing that you can do with your calculator. In this example, I've listed some starting salaries by degree. I looked up a bunch of different majors and found the average starting salary for a bachelor's degree in those fields. And I've listed them rounded to the nearest $1,000. So the 58 stands for $58,000 starting salary. I've listed a total of 15 different starting salaries based on the major that the students chose. What I want to do first is demonstrate the power of this 1var stats command by finding a bunch of different measures for this one set of data. Once again, I'm just going to edit to a point where I've already got the data into the calculator, and then we'll go from there. You may want to pause the video and type the data in yourself to run this along with me. So I've typed in the data. If you did it correctly, you should have come up with 15 total values. Make sure you have them all in there. So we're going to run the 1var stats command, and you'll see it will help us with all of these that we're being asked to find. I'm going to quit back to the main screen with second and the mode key. I press stat. I scroll to calc. Choice number 1 for 1var stats. I still have mine set up for the old operating system. If you have the newer operating system, you're going to scroll down to calculate and hit enter. Those of us with the older operating system can just hit enter right here. And we get a bunch of different information. The mean is around 57.53. I'll just round that to 57.5. The standard deviation, we have to have a bit of a discussion here because the calculator actually gives us two standard deviations. It gives us a sample standard deviation and a population standard deviation. Now, in this example, I didn't explicitly state whether this was sample data or population data, but as you're probably aware, there are more than 15 things that you can major in, and so this isn't the entire population. As such, we want to use the sample standard deviation for our answer, and so I'm going to round that to 19.6. So this data has a mean of $57.5 thousand, so that's $57,500, with a standard deviation of $19.6 thousand. That's $19,600. The median we don't see on our screen right now. We have to scroll down to get to it. You see that the median is 58, so that's a median of $58,000. And those are the three that the calculator will do explicitly. The other three the calculator will help us with. Like to find the range, we have to identify the largest and smallest value. And if you scroll all the way to the bottom, it will tell you the maximum. The highest starting salary in our list was $95,000. And we already scrolled past the minimum. The minimum was $28,000. So the range is calculated by doing 95 minus 28. And we have a range of 67 or $67,000 difference between the highest starting salary and the lowest starting salary in this list, in this sample. To get the mid-quartile in the IQR, we have to identify the quartiles. The quartiles are 41 and 73. So to get the mid-quartile, we do 41 plus 73 divided by 2. That's 114 divided by 2, which is 57. Note again that the mid-quartile actually fell really close to the mean and the median here. That indicates that there may be some symmetry to this data set. And the IQR is the difference in those. We always do the bigger minus the smaller. So Q3 minus Q1. 73 minus 41 is 32. And that tells us that the middle 50% of the data is spread out by about 32 units. Comparing that with the range, it's about half of the range, and so the data seems pretty evenly distributed. Again, indicating that maybe there's some symmetry to this data set. That one var stats command is really nice, but one thing it won't do is percentiles aside from the 25th, 50th, and 75th. So I wanted to demonstrate those one more time with this data set. We've got this sample data with 15 values, and we want to find the 20th percentile and the 70th percentile. Step one for both of those is to sort the data from smallest to largest. And you could do that by hand for 15 values. But I wanted to show you that the calculator can also sort your data. And since the data is already in the calculator, this will be an efficient way to do it. Let me show you how to sort data from smallest to largest in your calculator. The first thing you have to do is actually type the data in. I have the data in a list already. Now quitting back to my main screen. If I press Stat and look carefully, choice 2 says sort A. That stands for sort ascending. So I can put that on my main screen by pushing the 2 key. And then it asks me which list I want to sort. Well, I want to sort list 1. So second and the 1 key. When you hit enter, it won't look like it did anything. It'll just tell you that it's done. But if you go back to your list, Stat, choice 1, the list is now sorted from smallest to largest. And we can just poke around it once we figure out what locations we need to go to. To figure out the location, we calculate L. We'll do the 20th percentile first. The value of L is n times k over 100. N is the number of pieces of data, and don't reflexively put a 10 in there. I know that's what we used in the previous example, but we have more than 10 pieces of data this time. We have 15. Let's count just to make sure, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 pieces of data. Not 10. Sometimes people get the wrong impression because I do the first example and I use 10 for n in both of those cases, and they assume that n is always 10. But if n was always 10, I wouldn't call it n, I would just call it 10. N is the number of pieces of data, and here we have 15. We're finding the 20th percentile, so k is 20, and we divide by 100. This comes out to 3. That doesn't mean the answer is 3. Please don't put 3. A starting salary of $3,000 would not fall in this list. That's not a reasonable result. And you don't go to the third spot in this list or the sorted list. Remember, we're not using this list anyway. We're using the sorted list. But you don't go to the third spot either. You go to both the third and fourth positions. Let me pull up the calculator where the data is sorted. The number in the third spot is 38, and the number in the fourth spot is 41. So we find the mean of 38 and 41. That's 39.5. The 20th percentile is 39.5. We want to be careful about extrapolating this and saying that if you start at $39,500, then you make more than 20% of all college grads, because I only took a sample of some degrees, and of course there are some majors that have a lot more participants than others. And so you can't expect this to be a random sampling of all college grads. It's just a sample of some degrees. So be careful about taking this too far. The safe thing to say is that $39,500 makes more than 20% of the majors sampled here. Let's go over to the 70th percentile. So here we're looking at a situation where you're on the higher end. We again calculate L, which is still n times k over 100. N is 15, because there are still 15 pieces of data. K is now 70, and we divide that by 100, and that comes out to 10.5. That's not the answer. There's a step 3. You round this up to the next largest integer, and you go to that position in your list. We go to the 11th spot. So pulling up our calculator screen. As you scroll down, you might lose count, but the beautiful thing about the calculator is it tells you what position you're in the parentheses. The 11th number in list 1 is 63, and so the 70th percentile is $63,000. That 63 is bigger than 10 of the numbers in the set. It's bigger than everything that precedes it in my list. And 10 out of 15 is 2/3, which is 66.66666, right? That's around 67%. Which isn't exactly 70%, but if we went higher than 63 for our percentile, then we'd exceed the 70% that we were shooting for. So this is the best that we can do. So somebody who makes $63,000 is on the higher end. So make sure you practice this procedure by hand. Make sure you practice that 1-bar stats command, because it's going to be your best friend during the exam. Let me know if you have any questions.